topic of presentation is renewable energy microgrid installed at Medical Center, California. Renewable energy microgrid in hospital. Because healthcare facilities are most essential public infrastructure in any community. Illness and injury frequently require immediate access to care and cannot be delayed due to disruption in energy supply. Moreover, region is affected by high level of environment pollution and consequent health impact. The project also developed a novel microgrid controller that can island hospital life safety emergency power branch including emergency lighting and provide the power service during emergencies. During the non-emergency periods, the controller enables microgrid to achieve performance goals such as reducing utility energy consumption, site peak demand and utility costs with capability to participate in demand response. And this is the outline of the presentation: project profile, driving forces, design concept, component use, system installations, benefits of renewable healthcare microgrid project. The California Energy Commission awarded of $4.78 million grant to charge bills to design, engineer, build, and operate the first renewable energy for hospital in Kaiser Permanent Facility in Richmond, California, USA for the contract duration of 15 months. Installed capacity 50 kilowatt solar panel installed on the rooftop of a medical center's parking garage. One of the driving force is to generate the clean energy and to achieve the carbon neutral status. Further, it is to demonstrate the capability to support the continuous facility operation by islanding the microgrid during the utility power outage, and also to demonstrate the opportunity to reduce the hospital energy consumption, peak load, fossil fuel usage, and cost. Design concept is important for construction of any project. Failure to recognize and address each matter in step-by-step can result in unanticipated delays or design mistakes. So, during the course of project formulation, the team determines specific steps that must be taken in logical order to achieve project success. Therefore, following design concepts are adopted. Information of innovation nature of this project, it is essential to deploy experts for a variety of fields. A more robust team of people is needed to design tailored microgrid for hospital. More than 35 different parties collaborated to develop safe, feasible, effective design. Parties included mechanical, electrical, civil and structural engineer, communication system design, fire safety architects, battery and inverter contractors. Site characteristics. The team evaluated site energy loads, electrical architecture, operation objective, physical space constraints, possible points of interconnection, site geology, structure versus non-structure elements, relevant national, regional and local ordinance and regulation of serving unit. In addition to several site meetings to evaluate physical system, the team had a virtual meeting with all stakeholders to ensure project progress, strict adherence to regulatory requirements, and compliance with site tolerance and objectives. The technical advisory committee composed of all technical stakeholders provided additional commentary and recommendations to achieve success of project. Next, we have a microgrid engineering. Engineering representatives from supplier, contractors, facility and consultants collaborated to determine system sizing, control goals, point of intersection, monitoring, communication architecture, fire suppression and other systems. The components used in this project are 250 kilowatt solar panel, 1 megawatt hour Samsung batteries, phasor measurement unit, and Princeton PS3 port inverter. Once the project team received approvals from City of Richmond, the project installation proceeded in most linear fashion, including following steps: solar canopy. The solar power canopy panels were erected on steel canopy superstructure atop hospital parking structure. Solar panels 250 kilowatts were joined electrically to meet direct current voltage requirements of single centralized inverter, battery and inverter room. Concrete block wool battery and inverter rooms were constructed for heat isolation and long-term battery performance. The solar powers and Samsung batteries of 1 megawatt-hour were coupled to a Princeton power system inverter center utility plant. 6 specialized data acquisition devices called phasor measurement units were installed at critical monitoring points and connected to secure independent communication network to monitor system performance. Microgrid controller. Microgrid controller resides in the computer that are resistant to harsh conditions. These computers were located on site and at control design facility for purpose of system regulation, remote access and redundancy. Testing and commissioning. The testing and commissioning process were developed to evaluate individual systems with a microgrid as well as microgrid as a whole. The microgrid control is a direct current coupled microgrid. The most time was spent on inverter commissioning and tuning. First, inter-inverter controls were tuned to maximize the amount of solar energy. Second, communication and controls between battery system and inverter were verified through serial discharging and charging. Third, standard inverter functions, including output of solar generation, charging, discharging batteries, shutdown, restart, islanding were verified. Finally, the supervisory control was overlaid on an embedded inverter controller. Indicated in the figure, the mode of operation in normal and island mode. During the normal operation, the DG generator, which is indicated as genset, remain idle and disconnected while power is supplied from utility across the main meter and microgrid. Here, if AC port real power set point normally provided by supervisory control is less than PV power, then excess go to battery until high set of charge limit is reached. If AC power set point is greater the PV power, then difference come from battery until low set of charge limit is reached. The mode of operation island mode. When the utility energy supply is interrupted and power delivery is initiated from generator, the manual transfer switch to be repositioned to allow the microgrid to supply entire live a safety branch load in islanding mode. Here, PV energy is always prioritized. The load is supplied from PV and supplemented from battery. If load is less than the generated PV is used to recharge the battery. PV production is curtailed only if battery is full and available PV exceeds the load demand. At night, the PV converter section shut down to conserve battery energy and minimize the losses. The inverter requires battery to provide islanded power. If battery disconnect or shut down, the inverter will too. Benefits of renewable energy microgrid. Greenhouse gas emission reduction. The project is on track to produce between 365,000 kilowatt hours and 390,000 kilowatt hours per year of clean energy and reduce consumption of fossil fuel generation by 292,000 kilowatt hours per year through the safety and effectiveness. Resilience of critical infrastructure. The Kaiser Permanent Facility in Richmond, California now has added energy capacity to support emergency operations through microgrid-driven islanding of live safety power, cost savings and program development. The project is projected to save the hospital nearly 20% of its baseline utility costs. This substantial saving can be shifted to patient care program to sustain and grow healthcare service to an underserviced community. Dissemination of knowledge. Through the technical transfer activities, a broad range of stakeholders has become aware of the success of the hospital microgrid. In turn, this awareness has generated discussion with a new investor interested in supporting project development for the hospital system.